Welcome to my talk about communication saving algorithms in decentralized optimization. So this talk was originally given in UCLA Math 290J. This is a current literature seminar in applied mathematics, and it is organized by Professor Wu Taoyin. And this talk is just a reproduction of the talk at that time. So this is our outline. So we first introduce what is decentralized optimization and what we do with it. And there's a problem with it. First, introduce focus on primary algorithm to solve the communication problem with optimization. And we introduce motivation and do some formulation, and finally introduce the algorithm. And later we'll go a detour into the gradient sliding algorithms. We also introduce a motivation background and first apply it to composite optimization and then apply it to decentralized optimization. So what is decentralized optimization? In many machine learning applications, we want to solve this minimization problem where fi is usually some kind of loss, for example, least squares. And since we have a lot of data, we have to sum it into some form and minimize as x over some feasible set x to minimize our loss. There are a lot of ways to do this distributedly. For example, a very hot model and the main model we use in dentistry today is a centralized model, where we use the parameter server to hold one x. So the x is just one and only one. So each node will compute some gradient with respect to its own data and pushes updates to the server. However, we can also make it an equivalent formulation, which is called a decentralized model. And in this case, we don't have the same x kept on the server. Instead, we have it from W1 through Wn. So n copies of our parameters, and they could be different during the optimization. But our goal is to still minimize this sum of loss functions. And we add a constraint that W1 through Wn are all equal. So you can see that at optimality, the two problems are equivalent. However, since this Wi's could be different, that means that each node holds its own Wi. And it will compute and communicate with each other so that we reach on a consensus. And the consensus will be the optimal value. Here is a framework of general decentralized optimizations. So for each node, I, denoted by A, we simultaneously let them do this. Repeat these procedures. First, we do some gradient updates with its own data, and for some time, we regularly exchange some information with its neighbors. And we finally combine the information according to some combination policy. And the stopping condition will be consensus and optimality reaching together. There are some advantages and disadvantages of this. The pros are, first, we have perfect data privacy. This is especially the case when the nodes do not want to share the data with some server. For example, DeepMind, a Google company, has some ambition to solve the health problem with its own deep learning models. However, there are a lot of controversies because British government does not want to share all its patient data with DeepMind because it's a private company, and the British people do not trust in it. So yeah, there's a lot of controversies, and it really hampers the progress to a deep learning healthcare. In the second, the data privacy is kept perfectly because in this case, we don't have a server to hold all the parameters, and you don't have the hackers hacking to the server to steal all the parameters or data. And in this case, the security is kind of decentralized too, because each node will be responsible for its own parameters, and if you are hacked, that's only your responsibility. The data and parameters from other nodes won't be detected by just hacking your node. And the second benefit is you have localized parameters. So what does this mean? So we still go back to the hospital model I just mentioned about DeepMind. So imagine we have a lot of hospitals, and each of them has its own convolutional neural network model, and it has its own parameters to detect, for example, chest cancer. And in a centralized model where you have a server, for example, set up by the British government, you'll have the same set of parameters to detect the chest cancer across the whole United Kingdom. However, this is not usually what we want, and oftentimes the hospitals want to serve the patients from the local area more, and so the hospitals prefer to adapt its parameters and weights according to the local data. So this is especially true when the hospital have incoming data and the data is streaming to them. And as you can imagine, if you have a centralized model, all the parameters will be updated at once some patient data comes in. But in the decentralized model, exactly because you share the data only with your neighbors, the parameters from some node far away from you, like several degrees away, won't come to affect your parameters until sometime later, and the effects will be diluted because you will assign less weight to them. Also, the final one is a security one. You won't have server shutdown simply because you don't have a server. There are also some disadvantages of it. And first, you have more communication in total. This is a major problem we've talked about today, the solutions of it. But we'll talk about more later. Also, there's a problem is hardware support, because most of the hardware developed today are adapted for the server model, and you don't really have too many things to do in the real settings. There are already some algorithms developed decentralized models. For example, Extra, developed by Professor Watao Yin, and there's a diffusion algorithm developed by Professor Syed, also at UCLA, and there's a digging algorithm. And today we're going to talk about this focus on primary algorithm and gradient sliding algorithm. These algorithms are both proposed by Professor Guanghui Lan from Georgia Tech, and we also share some of our own thoughts about it. So we first talk about why we want to come up with communication saving algorithms precisely. So as we mentioned, there are some disadvantages with decentralized optimization. One is it requires more communications in total. So we think about the decentralized model where you have a parameter server and n workers will form n links between them. However, in the decentralized model, exactly because you don't have a server, the workers will have to share their parameters with more the workers. So, for example, each worker will have n neighbors on average. Then the n workers will form nd links between them. So that means you have nd like d times more communication, like in total compared to the parameter server. And another thing is, in theory, we can prove that if you have larger degrees, like larger d, so that each node will have more neighbors, then you have faster convergence. However, but that means d times more communication per iteration. And that could be a big problem when you have long delays and limited bandwidth on your communication. So can we design algorithms that reduce communication? So we first talk about this primal dual algorithm. First, let's jump to talk a little bit more about math, how we formulate the algorithm. There's something called combination matrix. So in our algorithm, we usually calculate at each communication step, we calculate the weighted average of parameters gathered from your neighbors. So in this case, Wi will get the sum of Aij times Wj. So Aij will be some kind of weight assigned to this node j by node I, and j will go over all the neighborhood of I. And as you can see, this pretty much looks like a matrix. Sorry, matrix multiplication, so we can assign all the aij into a big matrix called A, capital A. We can also stack all the wi into a matrix W. So the w1 through wn will be stacked together, and we essentially assemble all these weights from the whole cluster of nodes into one big W matrix. And in this case, the combination step will simply be wk gets a times wk minus 1 left. And also, by using this matrix, combination matrix, we can also state the consensus criterion easily. So we assume that A is symmetric. This is usually for theoretical convenience. We can also design it to be non-symmetric, but that's not the issue. But the important thing is A times 1 equals 1. So that means the null space of A minus this identity matrix will be the span of 1. So what does span of 1 mean? That means that if this bold font W lies on span 1, then we have W1 through Wn will be all equal. So the consensus criterion is also easy. We can just write this A minus 1, A minus I times W equals 0. And now we can formulate the primordial formulation of the problem. So we want to do the argument of this fw. So f, remember, is the sum of all the fi's from all the nodes. And this w will be also assigned to all these nodes. So it's just a kind of compact notation for the sum. So we want to argument this fw such that I minus a times w equals 0. So we want to minimize something such that the consensus is reached. So we can formulate the cluster Lagrangian of the problem, which is L of wy equals fw plus y transpose times this I minus aw. So how do we solve this problem? So each updates will be first yk gets this yk minus 1 plus 1 over the tau times 1 I minus k times this wk minus 1. And 1 over tau here will be our step size. And this wk will be the arg minimum of this weird thing. So it's kind of different from the like the usual iterative updates you expect from a Lagrangian gradient descent. And we'll talk about it a little later. So this thing, if you look at it, this is a Lagrangian where you have the fixed dual variable, and you add this something like a proximal term where you control the distance from your current point to the last point. And the kind of like a regularization parameter is this eta over 2. So the idea here is kind of simple. So since this communication involves I minus a, we want to only do like as few dual updates where you do the communications as possible. So we want to do single dual update, and then we do several primal updates. The claim is that we can save the communication at the cost of more computation where we do the argument stuff. So some people will wonder that compared to the regular iterative updates, why can we save more communication, the dual updates? Because there is always the bottleneck. If you only do this primal updates, you will finally get stuck by this dual variable. So now we introduce a focus on primary algorithm to do this. So the disclaimer: this focus on primary algorithm is not the original name proposed by Professor Land, but he doesn't name it, so I just come up with this name. So we look at the algorithm. We have an input, objective f, an initial guess, an initial dual variable, and all the parameters, for example, the number of iterations, and all these things. There could be time varying, but we'll see later. So in a major loop, this is a major loop from 1 to n. We do this. First, we we do an acceleration. I think this is a very important step. I'll explain later in a simulation result. And essentially what we do is, since we can only do one dual update, so we kind of want to make an estimate where we should do the dual estimate at. So by doing this acceleration, we kind of subtract this wk minus 2 from this wk minus 1 to get the difference from the last primal update. So assuming that we're searching in the right direction, this alpha times this difference plus this wk minus 1 will give you a rough estimate where you would get if you do the primal update. And then instead of using the regular wk, you use this wk underlined estimate of your primal update to do the dual update. And later you will do this regular primal update things. So notice that I did mention in the last slide that here, during the primal update, you actually have to do another round of I minus a times w. This is because look at the Lagrangian here, you have another I minus aw. So to do this, you essentially have to do another round of communications. So in each of the bigger loop, you're actually doing 2 communications. There's something to solve that, to reduce the communications. I'll talk about later. And so you see here, this part is essentially the Lagrangian, and this part is a proximal term. And this is our whole loop, the big loop. So to do this argmin stuff, you can use explicit solution if you have a very simple FW. You can also use gradient descent, SVRG, and that kind of things. And finally, in Professor Lan's algorithm, he also does this averaging thing. I think this is for purpose of theoretical convenience, and in practice, I don't see this is any good. It's good we just output this W capital N. And the output will be solution, which is this Wn. Now here I show how you do this if you use gradient descent to do this argument, to do this primal update. So here's the convergence result. So if we let this W star and Y star be saddle point of this Lagrangian, and we assume that F is convex and the primal update is solved precisely. And we set this alpha and theta to be 1, and this regularization and the dual update parameters to be something related to our network topology. And then for all n larger or equal to 1, we'll have this like the optimization speed, which is O of 1 over n. And we also have this consensus criterion, I minus a times Wn. We expect it to be 0 in the end, and it actually decreases at rate of O1 over n2. So notice that Professor Lan only provides theoretical results for F is convex, so we can't really improve this 1 over n here. This is quite similar to the results we used to have. We want to share some thoughts about this. First is that you do observe linear convergence on this algorithm when your loss function is strongly convex, and that is exactly as we expect usually. And the second one is the final averaging step. Remember, this step is not quite necessary. We always observe better results if we have the Wn, capital N, as soon as it converges, of course. And finally, we don't want to explicit updates of dual variables. So by doing this, we can save the communications. We can reduce the communications from 2 rounds to 1 round in each outer loop. So we can do this. So we eliminate this yk and use this v to keep track of the thing, keep track of the consensus thing. This trick is done because we have some spectral properties of I minus A, but we don't want to go too deep into that. And you can ask me if you are really interested in it. So by doing this, we essentially reduce half the communications, which is good. Also, another thing is we observe better results with S3G as an inner loop to do the argument thing than gradient descent to explicit solution. This is really weird, and we wonder why. And, if you're interested, you can email me to discuss further about this. Also, I want to show our simulation results on this algorithm. So we have the benchmark algorithm here as the exact diffusion. It was done by Kun Yuan et al. I think it's a very nice, very neat algorithm. Also, it converted exactly, so it's a very good benchmark to do a lot of things, and it's pretty simple to implement. So as we see, the blue line here is the exact diffusion, where you do kind of do the descent primal update and do updates one after another. And this orange line is a focus on primary algorithm. In this case, we fine-tune both algorithms to do the best, so we do not always oblige to the theoretical bound provided by Professor Lan, like alpha equals 1. We set alpha to be something different, but that's not very important here. But I just want to show that by doing this focus on primal thing, you're essentially, in practice, saving as much as 2/3 of your communication. So reducing this problem, which is the least square in this case, from 3,000-ish communications to 1,000 communications. And the loss here is on a log scale, so you see the linear convergence happen in both cases. There's also something I want to share too. This is so this one is when you have the regular focus on primary algorithm with acceleration, and yeah, it's pretty much the same thing as we saw before. However, if you just limit the acceleration, in this case, I'll set alpha, the acceleration parameter to be 0, then you observe something like this. So it's essentially it's as fast as exact diffusion, and nothing, like absolutely no improvements. Also, it does this kind of wiggling a lot because you're not doing primal updates as you are expected to do. So yeah, so it's pretty bad if you don't have the acceleration. So that's my whole point of this acceleration estimation. So now we go a little detour into the gradient sliding algorithm, and later we apply it to decentralized optimization. So what is gradient sliding algorithms? In many applications, we come back to single machine optimization. In many problems, we want to solve this argument of composite functions, where you have two parts. The first part is fx, and this one is usually smooth but expensive to evaluate. For example, least squares. It's expensive because it is usually involving something that requires computation over all of your data set. For example, 1 million data. And then you have this H term, which is non-smooth but cheap. For example, the TV norm or L1 norm. So it's kind of constraint or regularization term, and it only takes all your parameters instead of your all data to compute. So imagine if you want to do a 1,000 parameter model, then calculating hx will only require 1,000 evaluation with respect to each of the parameters. So imagine if you want to solve this problem, a kind of regularized loss function, we can do naive gradient descent, where the x plus denotes the update. So you want to update the x with this eta times this gradient f plus this subgradient h. I'm using this partial sign to denote subgradient because h could be non-smooth and non-differentiable, and you have to use subgradient methods on it. And the eta here will be the step size. And so there's some problem with the gradient, naive gradient descent. So if we only optimize fx or hx in this case, we actually could do much better than evaluating the gradients together. So if we do the arguing of fx, then because fx is usually like convex with L-Lipschitz continuous gradients, then we can do as few as 0.1 over square root of epsilon gradient evaluations of f, and epsilon here will denote something related to the precision you want to reach. So you want to optimize so that your optimum value will fall into somewhere near 0, that like less than epsilon. And this 0.1 over square root epsilon will be the number of gradient evaluations if you want to reach that target. However, since evaluating this f is expensive, so the total monthly computation is big. And if I do this h of x, then because h is usually not good, like non-smooth, non-differentiable, so the theoretical guarantee is very bad. For example, 1 over epsilon squared. So imagine your exponent is 10 to the negative 5. That will be 1 over epsilon squared will be something like 10 to the 10th. Whereas 1 over square epsilon will be something like 10 to the 3rd or 2nd. But since evaluating each gradient f, subgradient f is quite cheap, then that's not a very big problem. However, if you want to do naive gradient descent on this composite function, you have a nightmare because this fx and hx will be non-smooth, and evaluating their subgradient together will be quite expensive because there's a great f here. So you have 1 over epsilon squared gradient evaluations as the hx, but each of the evaluation will be expensive because of the f term there. So we wonder, can we do the gradient f and subgradient h separately? There are a lot of ways to do this, and a very famous one is a proximal gradient method. So in proximal gradient method, you still do the same problem, but instead of doing the gradient f and gradient h together, you do this proximal gradient. So what does proximal gradient mean? You first make an estimate of your x by only evaluating your gradient f. So x minus c times gradient fx. This is a usually gradient descent step if you only do this fx. However, because we want to take into account this hx, we also add this proximal term. So what does this proximal th do? It is defined as this argmin of u, h of u plus this 1 over 2t, and you want to control this u from control the distance between your u and where you reached in your last gradient update. So and then this essentially is like you want to minimize this hu, but you also do this soft projection onto your update after evaluating this gradient f. And using a little bit algebra, you can easily show that this form is equivalent to linearization of f. So this thing is actually the same as its argmin of u, linearization of f, which is essentially fx plus this gradient fx transpose times u minus x. It's like first order Taylor expansion at fx denoted like parameterized by u, and you add this thing to its h of u, and finally this kind of distance controlling term. So we have some. So in this case, we assume that h is simple enough so that this argument step will be solved exactly, like it has a exact solution. And so in this case, we only consider the complexity doing this f. So supposing f is convex with Lipschitz gradient and h is just generally convex, maybe non-smooth, then the complexity of it is O of 1 over epsilon. Oh, notice that this is not really related to the h because you're assuming that the argument step here can be solved in constant time. So this over 1 epsilon is the number of times you need to evaluate gradient of f. There's also improved version of proximate gradient method. Was proposed by Yuri Nesterov in 2007 and summarized by Paul Zeng in 2008. So this method uses this acceleration step with this parameter gamma. You do one acceleration first, and you do that. Do the same linearization thing, the same. So notice that this line is the same as the line here. So you do this proximate gradient in the middle, and finally you do another acceleration in the end. So this little trick, I don't want to talk why is that, it costs too long time, works, and it reduces the complexity from 1 over epsilon here to 1 over square root epsilon here under the same f and h constraints, f and h conditions. So this is good. However, this one also requires that you know how to solve this function in one step. For example, h is a least square or a L1 norm. You can do this. The problem is, what if the linearization step is not explicitly solvable? You don't have a closed form solution. For example, TV norm in image denoising. Okay, arguably TV norm has some special structure and you can still solve it easily, but there are a lot of regularization out there that does not, that you cannot find this good structure and you cannot find a closed form solution to this problem. So the idea here about gradient sliding is quite simple. So because you have this linearization of f here, so why don't we do another linearization of h inside this inner loop to do this argument? So we can fix xk underlying here in the LF of xk in our gradient method, accelerated gradient proximal gradient method, and we do another linearization of hu. So that we convert the minimization here into a series of linear problems with explicit solutions, because as you see, we do this and we convert it to this, and we use this ukt minus 1 to do the inner loop. In this case, these things, this f thing here and the xk minus 1 here will be the same, but we add this hu, we convert this hu into a linearization of h, and we add the corresponding proximal term here, and we use the pk to denote the extra regularization you have to do because you do this on this h thing. We can also add similar acceleration step into the inner loop to get better result and better theoretical convergence result. So let's look at the actual algorithm. The algorithm is simple. We first do the acceleration here and save our gradient f into gk, and in this inner loop we do the same, the double linearization of h as I mentioned before, and we add this proximal terms here to make it a proximal gradient method. And finally, we do this acceleration in the inner loop too. And at the end of outer loop, we save this ukt and we do the acceleration in the outer loop. So finally, we will output this solution xn here. So the theoretical result is quite similar. Suppose f is smooth, convex, and without Lipschitz continuous gradient, and h is non-smooth but Lipschitz continuous. We set this beta and gamma to be decreasing, so they're diminishing. Notice that beta is the proximal coefficient here, and gamma is the acceleration coefficient here, as well as here. Also, the another thing is we want to do this inner loop more and more. So t, notice, is here, this number of inner loops. So it grows at n times k squared. So that's a lot of numbers. But that's for theoretical convergence, you don't really need to do that much to observe good results in practice. And p and theta here, p here is the extra coefficient you want to do in a linearization in an inner loop. Also, you have this theta here, also diminishing, that corresponds to the acceleration in an inner loop. So all these things here are set, and we can have this 1 over n squared convergence. So notice that this is also the same result as we have before, because we are not really improving. We're not really improving the outer loop. We are working on the inner loop. However, the good news is that compared to the regular naive gradient descent, we have a much better result because now, exactly because you have 1 over n squared here, the number of gradient evaluation on f will be all 1 over squared root epsilon. So that's a good, very big decrease from 1 over epsilon squared if you have a naive gradient descent. And as we can see, we can apply this gradient sliding algorithm on the decentralized primordial formulation I mentioned before. So we still have this Lagrangian here, which is fw times plus this 1 transpose times I minus aw. So here, because fw evaluation is intranode, and this I minus aw is internode, so we want to save the communication, we just reduce this I minus aw. How do we do this? We can apply the gradient sliding algorithm to the inner loop of the focus on primal algorithm I mentioned before. So remember the argument thing I mentioned. If you don't have explicit solution to that problem, you can do this gradient sliding there. So the good thing is it deals with f with worse properties. For example, your f is not really good, and you want to do more, so your primal update will help you more than just doing like iterative updates between primal and dual. So reduces evaluations of gradient f. Also, since it's only concerning the inner loop, it does not save more communications compared to the focus on primal, original focus on primal algorithm. So remember, this is a focus on primal algorithm. I just copied the slide from the last time, and this is a decentralized gradient sliding algorithm. So we compare it, everything is almost the same, except that in this inner loop, you do another linearization. And finally, we have the convergence result, almost the same as a focus on primal. You're not saving more communications, and the convergence result is the same. That's the 1 over epsilon. However, if f is strongly convex, Professor Lan also provides theoretical results that you can do it in 1 over square root epsilon. But another time, if we eliminate the averaging step, we can do it like linear convergence. That's log of 1 over epsilon. And finally, we want to show some simulation results done by Professor Lan. This one is the conditional gradient sliding on matrix completion. So you can apply gradient sliding to a lot of gradient descent algorithms. For example, gradient sliding, conditional gradient is another form to solve the same composite optimization problem. It's quite similar to proximal gradient and quite related. I don't want to go too deep into that today. And the matrix completion problem here is you want to estimate your matrix to be close to your target matrix, and you have the F's there, which denote the closeness, how close you are to the target matrix, and the H there will be something, some penalty to, so that you can get a sparser matrix. And this is usually often helpful in many applications, for example, collaboration filtering and stuff like that. So this is the applying the gradient sliding to the conditional gradient and apply this algorithm to the matrix completion problem. So you see that this blue line here is a usual conditional gradient, and this red line here is a conditional gradient sliding algorithm. So it's much better than conditional gradient, and we're happy to see that. So finally, some references here. We mainly talk about these two communication efficient algorithms for decentralized and stochastic optimization. So the stochastic here, I didn't mention in this talk, is that Professor Lan also applies stochastic gradient descent to the gradient sliding and get better results than the usual one as expected. But that's not too different from the gradient sliding we talked today. So I just omit it here for clarity and the time. Also, the conditional gradient sliding. This is where the last feature comes from. And finally, all these papers are citing this original paper, Gradient Sliding for Composite Optimization. So this is the paper you want to go to if you want to know more about gradient sliding. Also, this accelerated gradient descent problem, accelerated gradient descent, proximal gradient algorithms I introduced earlier. So that's all. Thank you for watching, and if you have any questions, you can send me an email. Also, I have all the slides available on my GitHub, and this will be available in the video description. Thank you very much.